Welcome to this explainer. Have you ever actually stopped to wonder how we measure our certainty in a world that is just deeply uncertain? I mean, every single day we're out there evaluating risk, processing reality, and really trying our absolute best to figure out what's actually true. Usually, we just rely on our intuition and gut feeling. But what if there was a literal, mechanical, structured, mathematical way to do exactly that? A concrete framework for processing reality? Well, that is the fascinating concept we're going to explore today. And that brings us to a really interesting question. How do we mathematically change our minds? I know, it sounds kind of like a paradox, right? We typically think of changing our minds as this completely psychological, emotional, or let's be honest, sometimes just a stubborn process. But a core philosophical concept from our source material really challenges that perspective. It asks what actually happens to our deeply held beliefs, our initial assumptions, when we're suddenly confronted with brand new evidence. Turns out, there's a precise, logical architecture to changing your mind. It's not just about feelings anymore. It's about facts meeting probability. Okay, let's dive into this. The absolute key to that mathematical, mind-changing process is Bayes' theorem. Now, as our source defines it, this is a formula used for updating probabilities when new evidence is introduced. Just think about the immense power of that specific phrase for a second. Updating probabilities. It means we don't just establish a baseline, plant our feet firmly in the sand, and stick with our initial thought forever. No, we adapt. When a brand new piece of evidence lands on our desk, we possess a rigorous tool to recalibrate our entire understanding of reality. Now, I know the actual math might look a little complex at first glance, but I promise the mechanics of this formula are actually beautifully elegant. We have P of A given B, which equals P of B given A, multiplied by P of A, all divided by P of B. The core insight here, the real secret sauce, is the relationship between these variables. Specifically, how that inverse probability, P of B given A, helps us solve the whole puzzle. By knowing the probability of seeing this new evidence, if our original belief were actually true, we can effectively reverse engineer the math to figure out how true our original belief still remains. It's essentially a mechanism for weighing the strength of new clues against what we originally thought we knew. We can actually break the mechanics of this formula down into three really logical steps. Functionally, it's very much like a simple language translation. Step 1, you always start with your base probability, what the formula calls P of A. This is simply what you estimate to be true before anything new happens. Okay, step 2, you factor in the new evidence, P of B. The universe has just handed you a brand new clue. And then step 3, you calculate the updated probability, your P of A given B. So you've taken your initial baseline, you've processed the new clue, and you've arrived at a vastly smarter, mathematically sound conclusion. What's really interesting here is how these distinct concepts form a continuous loop of learning. You have the event, which corresponds to P of A, and that serves as your starting anchor. Then comes the evidence, P of B, representing the entirely new information that just disrupted the status quo. And finally, you get the update, P of A given B, which effectively becomes your new reality. So the crucial point is really how these elements interact. It's this ongoing, logical dance between what we thought we knew originally and what the data literally just revealed to us today. Moving into section 1, the medical test dilemma. To truly grasp the power of this theorem, we need to apply it to a deeply practical, real-world scenario. So imagine walking into a doctor's office for a routine checkup. Before any tests are even run, there's a baseline probability that you might have a specific illness. That's your probability before. Then, the doctor calls you a few days later with a positive test result. Suddenly, mentally and emotionally, you feel like you're facing an absolute certainty, right? But the profound secret that Bayes' theorem unlocks is that this positive test is absolutely not a 100% guarantee of illness. Instead, it's simply new evidence that comes in to disrupt and update your initial probability. Let's walk through it. First, you start with that initial baseline chance of illness, which is usually based on population data or your specific risk factors. Then, you receive that scary positive medical test result. But instead of immediately panicking, Bayes' theorem forces us to treat that result purely as new evidence, just a new variable to plug into our equation. Finally, you use the formula to bridge the massive gap between a startling test result and the actual true updated probability of being sick. The math quite literally forces you to pause, run the numbers, and arrive at a logical conclusion, rather than an immediate, knee-jerk emotional reaction. And this is exactly why our source explicitly emphasizes that medical test accuracy problems often use Bayes' theorem. This isn't just some niche mathematical curiosity. No, it is the fundamental underlying logic utilized by medical professionals, researchers, and statisticians to properly interpret diagnostic tests and evaluate those tricky false positives. It really showcases the real-world brilliance of this framework in fields that directly save lives and inform critical patient care. By evaluating new evidence this way, the medical field avoids jumping to inaccurate conclusions based solely on raw test results. Which brings us to our final thought. When faced with new evidence in your own life, how accurately are you updating your probabilities? Whether you're dealing with a medical test result, a sudden piece of breaking news, or a dramatic shift in your personal circumstances, are you reacting purely on instinct, or are you acting a bit more like Bayes' theorem? Are you systematically taking your base assumptions and carefully weighing the new evidence to find the truth? The mechanics of conditional probability offer all of us a truly fascinating blueprint for rational, structured thinking. So, the next time the world hands you an unexpected piece of data, how will you use it to change your mind? Thank you so much for exploring this explainer with me today.